Hello, I am Klaudia-Doris and this is Bernhard Stadler. We are both researchers at the ScaDS.AI Competence Center at TU Dresden. In this lecture, we will give an overview of state-of-the-art language models for code-related tasks and introduce some basic features of these models.
And in the second part of the presentation, we will address a few critical weaknesses of these language models and discuss possible research directions that could help alleviate these limitations.
The idea of automatic code generation is to support developers in different programming-related tasks to increase productivity. This can be achieved in various ways, for instance by enabling developers to specify instructions using natural language or by providing automatic code completion. All this with the aim of reducing the learning overhead and speeding up development.
Neural language models have shown impressive performance in natural language processing, and they have also become the basis for a growing number of programming-related tasks. However, classical language models are rather narrow experts that not only need thousands of labeled examples for training, but are also not particularly robust or flexible to even slight changes in data and task. Also, collecting labeled training data often involves a great deal of effort and cost. And this is true for natural language tasks already, but even more so for code-related tasks where programming expertise is required to correctly label a piece of code. Nevertheless, the amount and quality of training data are critical aspects that determine the performance of neural models.
To address these shortcomings, the prevailing approach now is to make use of massive amounts of freely available unlabeled data and pre-train language models in an unsupervised fashion. Then adapt the pre-trained model to a wide range of tasks with little or no modifications to the model architecture. In short, the trend points towards pre-trained large language models that can perform multiple downstream tasks.
This chart shows a timeline of the most popular large pre-trained language models and how their size has grown at an exponential rate over the past. Most of these pre-trained language models are based on variants of the transformer architecture, for instance BERT T5 or GPT-3. The only exception is ELMO, which has a recurrent neural network architecture. ELMO was introduced in 2018 by the Allen Institute for AI and is a large pre-trained bidirectional LSTM network of 94 million parameters for deep contextual word representations.
BERT was published 2018 by Google AI and is a bidirectional transformer encoder model of 350 million parameters that also learns contextual embeddings for words. The GPT models were introduced by OpenAI 2019 and 2020 and are high-capacity, unidirectional transformer-based language models of varying sizes of parameters. The latest OpenAI model, GPT-3, uses up to 175 billion parameters, which is more than 100 times the model size of the previous version GPT-2 with 1.5 billion parameters. These language models need very few to no examples to solve NLP tasks and perform equivalent or even better than the state-of-the-art models trained in supervised fashion.
In 2019, Google created an 11 billion parameter language model called the text-to-text transfer transformer, short T5, that combines all kinds of language-related tasks into a single text-to-text format.
NVIDIA introduced, together with Microsoft, one of the largest transformer models, namely Megatron Turing NLG, with 530 billion parameters. MT-NLG has 3 times the number of parameters compared to the existing largest models, including GPT-3. With MT-NLG, the authors introduced an efficient approach that enables training even larger transformer language models with hundreds of billions of parameters.
Some of the largest transformer-based language models in literature not included in this chart are the Chinese WuDa with 1.7 trillion parameters and Google Switch Transformer with 1.6 trillion parameters.
As the focus of this lecture is on code synthesis, we will give a brief overview of models for code-related tasks. In this chart, we compare different code models by their size, including popular models such as CodeBird from Microsoft with 125 million and Codex from OpenAI with 12 billion parameters. And also models like Tab9, which is already established as a useful code completion tool in different development platforms such as IntelliJ.
GPT-NEO-X, developed by Eleuther.AI, is the largest open source model with 20 billion parameters, and the recently published model by Austin and co-authors is the largest overall with 137 billion parameters. For a better understanding of code-related language models, we have summarized the most important features of some exemplary models in this table. In the following, we will briefly outline these features and then go into deeper detail later. The most important features are the tasks for which the models were trained, the underlying model architecture, the pre-training objectives, and the benchmarks and types of metrics used for evaluation.
All models except CodeBird are generative language models based on GPT, T5, or on a classical transformer architecture and use language modeling or masked span prediction as a pre-training objective. We will discuss the different types of pre-training objectives in a bit.
There are also a variety of code-related tasks with code completion and summarization among the most popular. Regarding benchmarks, there have been some recent changes, namely semantical evaluation has become more popular. That is, the focus is now on functional correctness rather than textual similarity. Not all the models shown are open source. For example, AlphaCode, Codex, and the commercial version of Tab 9 are not freely available.
To gain a better understanding, we will look at some examples of code-related tasks next, followed by pre-training and evaluation methods. There are a variety of code-related tasks that can be realized using language models. For example, code generation from a natural language input. In the example on the slide, the input statement is mapped to a corresponding code fragment, that is, a list comprehension in which each list element is incremented by 1.
Another task is code completion, which is also commonly used in development tools like IntelliJ or Visual Studio Code. In code completion, suggestions how the code can be completed meaningfully are made based on user input. In the example, the partially entered function definition is completed to a whole function with parameter list and function body.
Other common tasks are code translation and code summarization. Code translation is about translating programs from one language to another, for example, from Python to Java. Code summarization is about generating a natural language summary from a piece of code.
There are also many other code-related tasks like bug detection, program repair, code search, etc., which we will not detail further here. Language models like GPT-3 or T5 are pre-trained on large unlabeled corpora and then adapted to diverse NLP downstream tasks such as question answering, common sense reasoning, or code-related tasks. The transfer to a downstream task is achieved either by supervised fine-tuning using a task-specific labeled dataset or by prompting in a 0, 1, or few-shot manner.
On this slide, we show the basic idea of fine-tuning a pre-trained model, that is, transferring what was learned in the pre-training phase to a downstream task such as code translation or code summarization with additional training. This can improve the performance of the model and shorten training time.
Technically, it can be implemented in the following way. A neural network consists of several layers, each of which transforms its input according to a set of numerical parameters, until finally an output layer is reached. Training a network means finding parameters for every layer, such that the output layer produces a result as close as possible to each training sample's expected output.
In transfer learning by fine-tuning, the parameters learned during pre-training are copied to a new model with similar shape. In some cases, parameters are reinitialized, for example in the output layer, or new layers are added. Then training is continued in a supervised manner, but with the downstream objective instead of the pre-training objective. For the code-related language models, we show 3 types of pre-training objectives that are also used in the underlying language models such as GPT-3 or T5.
The first pre-training objective is called language modeling. It is used, for example, in Codex and in other GPT-style language model. It consists in learning to predict the next token given a prefix. In the example, this would be the token 1. This objective enables autoregressive generation during inference, that is, predicting a sequence token by token from left to right starting from a given prefix.
The second pre-training objective is masked language modeling and is used for classification tasks. This objective is used in BERT-style models such as CodeBERT. The masked language modeling objective works as follows. Given a sample of the pre-training dataset, with some input tokens replaced by a special token MSK, the model learns to predict the original values of the tokens in these masked positions. In the example, this would be the token I.
For the third pre-training objective, masked span prediction, not only single tokens are masked in the input, but spans of several tokens. The model learns to predict each masked span preceded by its corresponding masked token. In the example, it would have to predict the span incremented by for the first masked token MSK1 and the span 1 for IN for the second masked token MSK2. This objective is suited for both generation and classification and is used in T5 style language models such as PyMT5 or CodeT5.
To evaluate and compare different models for code generation, we need both freely available evaluation datasets and suitable metrics. So far, there is no one-size-fits-all metric that the whole research community has agreed on.
All evaluation metrics for program generation are essentially similarity metrics, which means that they compare generated code with reference solutions in some manner.
As a broad distinction, there are textual and semantical metrics. Textual metrics look at the surface structure of the code, whereas semantical metrics consider the meaning of the code and evaluate its actual behavior.
Textual metrics such as blur and exact match accuracy are easy to compute, but they only interpret the code as a sequence of token or as syntax trees and therefore cannot capture its meaning. So identical code behavior does not always result in high similarity scores.
Semantical metrics come closer to the meaning of the program, and depending on whether it's a static or dynamic metric, such as passAtK, execution of the program code is required, which in turn requires an isolated execution environment.
As datasets for evaluating code synthesis models, several benchmarks have been published in the last few years. As an example, we show only the human eval dataset that was introduced by OpenAI together with the dynamic metric passAtK. The human eval benchmark consists of 164 handwritten Python programming problems with an average of 7 to 8 unit test cases per problem. Each sample consists of a prompt containing a Python function signature and a documentation string, a suggested implementation of the function, and a unit test.
The functional correctness of the generated code is evaluated through unit testing using the passAtK metric. Computing passAtK means generating candidate solutions per problem, and if any of them passes all unit tests, then the problem is considered solved.
We would like to conclude the first part of this presentation by outlining a few critical weaknesses of language models for code synthesis.
Large language models are pre-trained using an unsupervised training task that consists in reproducing the code as it is found in the data. This also includes any bugs, bad programming style, and anti-patterns. But even with a clean code basis, there is still a gap between the objective the model was pre-trained for, the end user's actual intent, and the model's effective behavior. This gap is known as AI misalignment. Also, there is no guarantee that the model generates syntactically correct and executable code. Besides, current models have no conception of the meaning of the generated programs beyond what can be learned from the lexical structure of the code.
Moreover, when we specifically use adversarial patterns or intentionally avoid using patterns during evaluation. Models struggle or fail completely on tasks such as simple common sense reasoning or simple math word problems, which shows a significant weakness in reasoning. All of this poses some serious safety-related risks.
As pointed out, a critical weakness of today's language models is reasoning. Reasoning is crucial for understanding the user's intent and the meaning of program code. For instance, GPT-3 struggles with tasks that require mathematical or common sense reasoning, like solving math word problems. Thus, the goal is to design general-purpose language models that capture systematic reasoning and are able to generalize algebraically. This means we need models that don't only learn shallow tricks based on simple patterns in their training data, but that can actually understand to do algorithmic manipulations of values.
Autoregressive models, which generate each solution token by token, have no mechanism to correct their own mistakes and to learn from them, and one subtle mistake is enough to derail an entire solution. To match human performance in complex logical domains, it has been argued that models need to develop an understanding of their world and to be able to navigate abstract ideas and recognize and correct their mistakes. And this would apply a more general AI that is a self-aware system in some sense. It has been argued that simply increasing parameter counts and computational budgets will be impractical for achieving strong mathematical reasoning. To have more traction on systematic problem solving, we would likely need algorithmic advancements from the broader research community rather than only larger models. Further research could explore how the inclusion of symbolic and structural knowledge could help alleviate reasoning limitations. We made an attempt in this regard that we would like to briefly introduce.
The attempt we made to incorporate structural knowledge into language models is to use an encoding scheme that makes it easy for the model to take the hierarchical structure of code into account.
The basis of this encoding scheme is the abstract grammar of the programming language, which defines how a program is structured, for example, into functions consisting of statements and blocks of statements in a certain order.
Beside encoding hierarchical information, we also use this abstract grammatical structure of the programming language to keep the model from producing code that is not valid.
We implemented the hierarchical encoding scheme in a transformer-based language model that learns to map natural language specifications to a tree-based representation of the output code. The output code can be any meaning representation such as logical forms, for example, lambda calculus expression, or a general purpose programming language like Python.
The only requirement is that the output can be represented as an ordered type tree. Then an abstract tree representation can be derived from it, which is composed of object, attribute, and special nodes, as shown in the example on the slide. We use this abstract tree representation to encode positions within the hierarchy, replacing the flat positional encoding scheme of the standard transformer architecture.
More specifically, to encode these positions in the tree representation of a code snippet, we rely on edge paths. An edge path consists of the edge indices of the edges on the path from the node up to the root node. Each node is uniquely identified by such an edge path.
We apply a sinusoidal encoding to each edge index of a node's edge path, concatenate the individual encodings, and add them to the node's embedding.
We have integrated our code generation model in a dialogue system named CodeKai for supporting data scientists in the implementation of analytical workflows.
With CodeKai, data analysis can be specified using natural language instructions, which are then automatically translated into executable Python code snippets.
For the realization of CodeKai, we used the dialog system framework RASA. We integrated CodeKai into the Jupyter Lab data science environment as an extension through which a dialogue with the conversational assistant is possible. The conversational assistant can invoke the language model to generate code into a Jupyter notebook.
In the following, we will demonstrate in a short video how a data science task can be performed with CodeKai. First, we ask the assistant what machine learning methods are available. The assistant offers some options and we choose k-means clustering. As we don't remember what parameters are required for k-means, we ask the assistant. We don't have a dataset at hand, so we generate a random one. The assistant added some optional parameters we don't need, but we can edit the code to fit our needs. Now, we create a k-means model and then start the training. Finally, we tell the assistant to visualize the clustering as a scatter plot. To conclude this talk, the trend points towards pre-trained high-capacity language models that can be adapted to a wide range of tasks, including code synthesis. Still, the current state of the art has not yet reached the point where an AI can reliably generate working code of high quality for a wide range of programming tasks. But AI-based code generation is already doing amazing things and has started to become the basis of useful products for generating boilerplate code and speeding up prototype development. A prominent example here is Copilot from GitHub, which is built on top of OpenAI's Codex model, but also other already established code completion tools like Tab9.
Code synthesis from language models cannot yet keep up with the quality standards of formal methods such as program synthesis from logical specifications or from domain-specific languages. Program synthesis from logical specifications has its application mostly in areas where programming areas are costly or dangerous, and domain-specific languages in domains that are very well understood.
The challenge is now to build bridges between both worlds. The immense knowledge contained in large pre-trained language models on one side, and the mathematical precision and safety of formal methods on the other. In the future, it should be possible to combine the ease of use and implicit knowledge of pre-trained language models with the mathematical precision of formal methods for high-quality code synthesis.
We would like to extend on this work by finding new ways to utilize symbolic and structural knowledge in pre-training and fine-tuning language models. The goal of this thread of work is to improve the model's reasoning capabilities and their grasp of the meaning of programs. This concludes our presentation for the ScaDS.AI Living Lab lecture series on language models for code generation. Thank you for listening.